Welcome to Astronomy for Everyone. I'm your host, Steve Whitty, and with me today is our guest, Mike Simonson. Mike Simonson comes to us from the AAVSO. He is a leading variable star observer and advocate with over 94,000 observations since 1998. He is employed by the AAVSO, and he has a special research branch. Welcome to the show, Mike.
Thanks. Nice being here.
So I think we'll get the ball rolling with what is the AAVSO?
Well, AAVSO is an acronym for the American Association of Variable Star Observers. It's a nonprofit science organization that collects and archives variable star data for scientists and educators and students and researchers to use to study stars.
So I know you from Michigan, but the AAVSO isn't here.
No, the AAVSO is headquartered in Cambridge, Massachusetts. So I work out of my home remotely, but my office is actually physically in Cambridge, Massachusetts.
But you make a bunch of trips to Boston.
Yeah, I travel quite a bit.
So, all right, so the V in AAVSO is variable. What are variable stars?
Variable stars are stars that change brightness for a number of reasons. Many of them have to do with stellar evolution. The secret lives of stars is basically what we're involved to a high degree. So when stars are first being born, they haven't settled down into a normal star-like state like the sun. They're highly variable when they're first being born. As stars evolve and get older, they start to puff up and turn into red giants, stars like the sun, and then they become variable. They actually pulsate. There are other stars that are variable because there's actually two stars rotating around each other, and as one passes in front of the other, from our point of view, you see one of them dim, and those are very interesting to scientists because they can actually determine the mass and size and a lot of things about those stars because they're variable and because you can actually see things happening with them physically. And then other stars are stars that die in horrendous explosions that destroy them, or they leave behind remnants, like nebula or white dwarfs or other degenerate forms of stars that are the last cycles of stars' lives. So basically, almost every star is going to be variable at one point in time in its lifetime or another, and so we're basically studying the secret lives of stars, like I said.
So how long has the AAVSO been collecting data, doing this sort of stuff?
Formally, since 1911, but actually a little bit before that. It started as part of a project with Pickering at Harvard College, and he got a bunch of amateur gentlemen astronomers back then. So kind of unusual. You see these pictures, all these guys with their telescopes wearing ties and bowler hats and stuff. And they actually started collecting data for him on stars that they knew were variable.
So well over 100 years.
Mm-hmm.
So in 100 years, stellar evolution does what?
That's really short time scale for stellar evolution.
So
we have actually seen stars that we think, we've seen events in their lifetime, in our lifetime, that are part of that cycle. But it's kind of like being an ant in the forest. You see old trees lying on the ground, and you see acorns, and you see little trees just sprouting, and you see full-grown trees. And you'd have to be a long-lived ant to understand that the acorn and the little tree and the big tree and the one that died and fell over are all really the same thing.
But if you had 100 years and you had a lot of stars, presumably you could be lucky.
Yep, a lot of it is serendipity.
So let's see. So let's go into how you make a variable star observation.
Okay, what we do basically is we compare the brightness of the star that's the variable star to the other stars on a chart that we make special for this job that are not variable. And we know precisely how bright they are. And so you pick a star that is slightly brighter and one that is slightly fainter, and you sort of make a judgment call in between the brighter and the fainter one to determine what the star's brightness actually is. So if there's a variable that's about 11th magnitude, say, in brightness, you might want to pick a star that's 11.5, which is slightly fainter than 11th magnitude, and say one that's 10.8, which is slightly brighter, and then you judge it just like judging the gas gauge in your car. You know, is it a little closer to the 10.8 or is it a little closer to the 10.5? And you make the call, and you write it down, and you log the time of the observation, the name of the star, and you send that data to us, and we can create light curves, and we keep all this information handy. People also do much more precise measurements with CCD cameras and photoelectric photometry, and now DSLR cameras too. And we provide them with photometric sequences, which is basically the star chart plus a bunch of fancy numbers that tell the different colors and brightnesses of the stars in different wavelengths.
But back to doing it manually, does it take a day or two to get a feel for how to do that? Or
it took me about 2 weeks to actually make my first variable star observation.
Okay.
Everything bad that could possibly happen happened in those 2 weeks, including losing a pen in the snow and some eyepiece covers and some other things. It didn't take me long to figure out I didn't like doing it outside. I wanted an observatory.
Yeah, all right, so we'll call it 2 weeks a maximum?
Yeah.
Try to do it in the summer where you're comfortable rather than in the winter for the very first time?
Fall's a really good time because in the summer it doesn't get dark until late.
That's
so
right.
You have to stay up really late to get started. So start in the fall when the weather's nice, and by the time winter gets around to us, maybe you'll actually have your feet wet and be doing it.
And this is a November show. This is kind of the fall, right? It's certainly dark early.
Yep.
Yeah, it's my favorite time.
Yeah, mine too.
Yeah. So what is your special area? Oh, I wanted to do one more thing. Let's say you live in downtown Detroit. Can you make variable star observations?
Yes. In fact, two of my best friends, one lives in Birmingham, England, and it is so light polluted there that his sky is actually orange at night. Okay. And he's one of the leading variable star observers in the world.
Mine is too, by the way.
Yeah. And another friend of mine does basically naked eye and binocular variable stars from on top of his apartment building in Buenos Aires.
So you can do this with as little equipment as you go out and look.
Yep.
But if you want to look a little fainter, binoculars.
Yeah, it just depends on what equipment you have. We have something for everybody. Betelgeuse, which is, a bright orange star in the constellation of Orion, one of the brightest stars in the sky, is a variable star. And you can actually make observations of Betelgeuse naked eye and compare it to other naked eye stars in the region of the sky and submit your data to the
Orion's
AAVSO.
a bright constellation. There are a lot of bright stars out there.
Yep.
Rigel is like ridiculous.
Yep.
Yeah. All right. So then what is your special area of interest?
Well, my special area of interest is a subset of a group of stars called cataclysmic variables. And they're stars that are a red dwarf star, smaller than the sun, about the same mass as the sun, maybe a little less, and a white dwarf star, which probably is a little more massive than the sun, but it's in a very small state. It's probably only about as big as an asteroid or a small, country, say. In fact, if both of these stars rotating around each other would probably fit inside our sun. They're so close together. And what's happening in these systems is that the white dwarf is the primary. It's the one that weighs the most or has the most mass. And it's actually so close to the red dwarf that it's stripping material off of the atmosphere of the red dwarf star and trying to grab it for its own. And what happens is this material that it strips off can't crash right out onto the white dwarf. It has to sort of go into orbit around the white dwarf. And it creates what we call an accretion disk. So the white dwarf is accreting material from the red dwarf. It turns into a disk around this white dwarf star, and eventually this builds up to a certain mass and viscosity that it crashes down onto the surface of the white dwarf, and suddenly a star that you couldn't even see in a 12-inch telescope because it's too faint now becomes a 10th or 11th magnitude star that you can see with binoculars or a very small telescope. So they, in a matter of hours, become thousands of times brighter than they were last night even. So this happens very quickly. And these stars do this, on different time scales. Some of them, they go into outbursts. This is what we call it when they have these eruptions. Some of them, it happens once every week or once every couple of weeks. Some you have to wait 30 or 40 days for it to happen. Some you may wait several years in between outbursts, and others actually take decades for it to happen.
And these outbursts are what we're talking about for cataclysms?
For cataclysmic variables, yes. Oh. So they're a special subset of those, all those different variable stars that we were talking about. These are really close binary systems where they have this geometry of a red dwarf, a white dwarf, the accretion disk, and they have these outbursts. And it's a lot of fun to observe these stars because you never know what they're going to do. You can't predict when they're going to go into outbursts. So you can be watching a star night after night after night and not even see it. Part of the observation is it's too faint for me to see. And so you actually record that it's less than the faintest star that you can actually see in your telescope that night. And then suddenly one night you go out to the telescope and you get to that field and you're thinking, well, it's probably not going to be. And there it is. And, I remember the first time I saw SS Cygni in outbursts, I almost fell off my observing stool because I didn't expect it to be there, and there it was. So is that kind of exciting.
So is that a case where you might make another observation later in the night?
Yeah, in fact, SS Cygni you can actually make, because it's almost circumpolar, you can make an outburst at the beginning of the night as it's rising, and then you can make another observation just before it sets on the other side, several hours later, and it may have changed in just that short amount of time.
Wow. Well, so we're coming up on the end of our first segment. So at the bottom of your screen is our email address. We like to see email. Send us a note, send us a question, send us a comment. We'd love to hear from you. And with that, we have Term of the Month with Don Glaser.
Thanks, Stephen. Our term of the month for November 2016 is apparent magnitude. The apparent magnitude of a celestial object is stated as a number indicating its brightness as seen by an observer here on Earth. Now, it's an inverse relationship, so the brighter an object, the smaller the number. The system was originally put into place by the Greek scientist Hipparchus back in the 2nd century BCE. Now, he only included the stars, and his numbering system went from 1 to 6, 1 for the brightest, 6 for the dimmest. Centuries later, when they wanted to expand his system to include brighter objects such as the sun or the moon, they didn't want to undo his previous work, so they instituted negative numbers for these brighter objects. Our sun is a -27. Apparent magnitude, our term of the month for November 2016. Stephen, back to you.
Thanks, Don. In this second half with our guest Mike Simonson, we're going to pick up more or less where we left off with Z-cams. So, Mike, we sort of introduced what a Z-cam is. Let's get into it.
All right, well, Z-cams are actually a subset of the cataclysmic variables we were talking about before, which are known as dwarf novae. And most cataclysmic variables spend most of their time at a faint level, and then they go into outburst. But Z-cams, they don't do this. They're a little bit different. So Z-cams actually have what are called standstills, where they'll go into outbursts, and then they'll get faint again, and they'll go into outbursts, and then occasionally they'll get stuck at a point in between, and they'll stay there for weeks or sometimes months, even maybe up to a year, before they start resuming their normal activity. So if you look at a light curve, like the one on the screen, you can see that these stars are very active, and then all of a sudden they stop. It's almost like the patient died on the table, and then it gets revived, and it starts going again. So that's the definition of a Z-cam. Yeah. If it doesn't have those standstills, it's not a Z-cam, it's just a dwarf nova.
So the name Z-cam, where does that come from?
It's from the name of the original star that was first discovered to be this kind of star, Z Camelopardalis.
So that's the giraffe, not the camel, the giraffe constellation, and Z is which star it is.
Yep.
Yeah. So, all right. So,
how did I get? How did I start this campaign, the research project?
Yeah. Why did you? What drew you to this sort of campaign?
Well, I'd been watching a bunch of these dwarf nova for years, and I knew about Z-cams, and I saw this one star that became the inspiration for this project. It's called AB Draconis, another star in the northern sky in the constellation of Draco. And I had seen it doing this activity over and over again, going up and down and into outburst and back to quiescence, but I'd never seen it go into standstill. So I wondered why everybody said it was a Z-cam. If it doesn't have standstills, it's not a Z-cam. So that kind of got me looking at other stars that were purported to be Z-cams, and a lot of them didn't have standstills. And so I wondered, well, what was going on here? And it turned into a detective story. I had to go back to literature all the way back to the early 1900s to find out what had happened. And long story short, the definition of what a Z-cam was had changed over the years. The first couple of cataclysmic variables, dwarf novae, that were discovered were U-Gem and SS Cygni. And U-Gem spends most of its time quiet. If you look at a light curve of U-Gem, you see mostly it's down about 15th magnitude, and every once in a while it goes into outburst, like once every 150 days or so. So maybe once or twice a year it has an outburst. SS Cygni was discovered shortly after, and it has a lot shorter time between outbursts. It's a much more active star, but still it spends most of its time in quiescence, quiet. Z-cams they discovered early on, and a couple more stars, RX Andromeda, Z-cam, a couple others were discovered in the early 1900s, and they never spent time in quiescence. They were constantly going up and down and up and down. There's a light curve of Z-cam from the 1930s that shows exactly this. Those are visual observations recorded by visual observers, and the star, as you can see, unlike those other ones, it's hardly ever still. It's always going up and down and up and down.
There's no flat anything.
No, except you can see in that light curve there's a little bit of a standstill in it. But originally, that was just an unusual feature. It wasn't the defining characteristic of what a Z-cam was. So any star that had this hyperactive personality became a Z-cam. Later, over the years, the definition developed into the 70s. It finally became that the standstills were the determining characteristic of Z-cams. So what had happened was, you know, some of these stars that were hyperactive aren't really Z-cams. They're just dwarf novae. But we had to sort this all out, and that's what this whole campaign was about.
So you winnowed down the list. It's no longer the full original list.
No.
So you got rid of a bunch. So those are outliers.
Yep.
You've got a new definition. It's a more robust definition, and you've winnowed it down to just the ones that meet that criteria.
Yeah, of the 69 stars that we began studying in this campaign that were at one point or another, or still today, considered to be Z-cams, we got it down to 22 that actually were Z-cams.
Wow, it's only like a third.
Yeah, which to me makes them even that more interesting because they're really a small subset of these dwarf novae.
They're more rare. Yeah,
exactly.
They're rare. Yeah, awesome.
So when we started the Z campaign, we had 5 objectives, and they're up on the screen. We wanted to determine which of these stars actually were Z-cams and which ones were imposters. We wanted to improve the overall data because some of them we couldn't determine whether they were Z-cams or not because there just wasn't enough data. So I wanted more people to look at them more often so we could get better data.
And over a couple of years or so,
Yeah.
you could get better data.
Yep. We've
Awesome.
been working on this for almost 8 years now. And one of the other things that we wanted to find out was there was a hint in some of the data that some of these stars actually, when they went into standstill, could occasionally go back into outburst and then go back into standstill. And according to the theories of CV accretion theory, that's impossible to happen because all the material from this accretion disk has already dumped down onto the white dwarf. So where's the energy and material come from for a new outburst in the middle of a standstill?
And if you've got a lot of people looking at the star, frequently, then you can catch it doing something weird.
Right, and we found 9 of them that actually do that. So of the 22 that we verified were Z-cams, 9 of them, almost half, do this too. And we also wanted to find, and that became very important because that kind of really screws up the models of CV accretion in many ways, as we've thought about them for the last 50 years or so. And then we also thought one of the things we wanted to do was just, if we're going to be looking at all these stars this intently for this long, something is probably going to pop out that we're not expecting. And so we figured we'd discover something through serendipity. And we did. We actually discovered a new type of Z-cam star that nobody can understand what they're doing right now. They're a total mystery. In fact, they're now called anomalous Z-cam stars, and there are like 4 of them now.
So anomalous just meaning,
for lack of a better name,
you don't know what they're doing.
We don't know what they're doing or why, but they are all very similar in their light curves and in their behavior and the time frame that this behavior happens and everything.
Are there other ways to? Oh, I wanted to get back to If you're when you're doing these rapid observations of a star, really what you're getting is time domain observations. You know, you can get spectral domain, that kind of stuff, but time domain is something that, I mean, we could call it new to astronomy, even though we've been doing it for 100 years.
Right.
One of the observatories that's coming up is going to give us a fire hose of data.
LSST.
The LSST, the Large Synoptic Survey Telescope. Yeah. And it's a huge telescope. It's going to look at the whole sky like every 3 nights or something.
Right.
Time domain, you know.
Yeah, we'll be drinking data out of a fire hose.
Right. So we're still preparing for this. We know it's coming.
Mm-hmm.
Yeah. But the AAVSO is kind of used to that. The data is coming in pretty fast.
Yep. And it gets even more intense. I mean, every year it's kind of a log scale. The pitch of the numbers of observations that come in. You know, it used to be a few 100,000, then 500,000, then 1 million, then 2 million, and we keep getting more and more data from our observers.
Yeah. So let me see. We were on Z-cams.
Yep.
We had the weird ones.
Yeah, the anomalous Z-cams. And you were talking about time domain too, and I wanted to bring this up. Is one of the reasons why I was particularly interested in Z-cams was because a lot of time has been spent on other subsets of these cataclysmic variables that you need to watch them like once every minute and record with a CCD camera or something, so that you can actually see these things called super humps in their light curves. But that sort of excludes visual observers from the research. With Z-cams, we really only need one good observation a night. You know, 1 point a night that's accurate, or a bunch of observations over a week that we can, whittle down to create a light curve, is still very valuable. And so this was a perfect project for AAVSO observers because we could use visual observers and electronic, sensor observers with CCDs and everything to combine their data to get better data for some of these stars.
Yeah. Well, presumably the pros have looked at some of these stars with spectroscopy.
Yeah, that was what they tried to do to determine what was going on with the anomalous Z-cams. and their results were inconclusive. They couldn't determine spectroscopically anything other than that they're dwarf nova.
So maybe a big scope in space, like the Webb in a couple of years.
Possibly. My theory is that it has something to do with these red dwarfs because they have all these spots all over them. The red dwarf in one of the nearest cataclysmic variables, SS Cygni, is reported to have maybe up to 60% of its surface covered in these spots. And they throw off flares and do all kinds of weird magnetic things that could possibly disrupt this accretion stream that's flowing onto this white dwarf.
Oh, that's interesting.
So, if it has anything to do with gravity, it's probably going to be very strictly periodic. And these things are totally unpredictable, so I don't think it has anything to do with gravity. So if you eliminate the accretion disk and the white dwarf, because they don't really do anything, just sit there and cool off over millions of years, the only thing really left is these ugly red dwarfs with the spots all over.
So maybe some theorists with big computers will do the magnetohydrodynamics that you need for modeling.
Yeah, well, we need to be able to see the red dwarfs too, and
that would be nice.
If you could weigh them and you knew how the relative, difference in mass between the red dwarfs and the white dwarfs and the total geometry of the system, that might give you clues too. That's probably a little beyond what the amateurs can do, but we can at least set up the thought experiment and get the data for which stars they should bother studying. Because if you've written a paper on Z-cams in the last 20 years, you've probably included in your set of stars that you studied a whole bunch of stars that aren't even Z-cams.
Right.
So your research is sort of brought into question at this point.
Yeah.
So many seminal papers on Z-cams really aren't that relevant anymore because they used half of the sample was stars that aren't even Z-cams.
Yeah. We're almost out of time. Any last minute things that you'd like to say?
No, just that the Z campaign continues, and we've actually published a lot of results ourselves in peer-reviewed journals. It's been very successful, and I hope it keeps going for many more years. It's a very interesting thing. It's something amateurs can do to contribute to science, and they're screwy, unpredictable stars. So what could be more fun?
Citizen science. We love citizen science.
Absolutely.
It's great having you on the show, Mike.
It was great being here.
Yeah. So at the bottom of your screen, we have the website from the club. This is where you can see links to all of our shows up on YouTube. And we also have a link for the AAVSO. So it's aavso.org. You can easily remember it, but write it down and give it a look. There's lots of stuff there. And we close the show by having Don do What's Up in the Night Sky. Off to you, Don.
Thanks, Stephen. What's up for November 2016? We'll begin with the phases of the moon. The first quarter moon arrives on the 7th of the month, the full moon on the 14th, and not so coincidentally, the full moon will also be at perigee. That's when it's closest to the Earth in its orbit, which will make the November full moon the largest for 2016. It's also interesting to note that the next night on the 15th, the almost full moon will pass right by the Hyades, the star cluster that forms the face of Taurus the Bull. The third quarter moon is on the 21st, and the moon is at new when it's between the Earth and the Sun on the 29th. Now, for our star, the Sun, sunrise on the 1st will be at 8:07 a.m. and sunset at 7:42. However, by the end of the month, the sun will rise at 6:26 and set at 5:02. Now, if you're wondering why the great discrepancy, remember, we go back to standard time on Sunday the 6th. Now, for the planets, we'll take a look. These are all at the end of the month on the 30th. Here we can see Mercury, Saturn, the Moon, and Venus. Now, Mercury in mid-month will be visible in our evening twilight sky. Venus sets at 7 p.m. and Saturn sets at 6 p.m. In our next image, we can see the outer two planets of our solar system, Uranus and Neptune, along with Mars. Now, Mars is a naked eye object. You can see it just looking up. And at mid-month, it will set at 10 p.m. We can see that Uranus is in the constellation of Pisces and Neptune in Aquarius. Our last image is of Jupiter, again on the 30th, and it can be seen in the morning at about 6 a.m. In November, we have two different meteor showers. The first one is called the Taurids, emanates out of the constellation of Taurus the Bull. It's actually in two parts, a southern part and a northern part. Now, the southern part is at its peak on the night of November 4th into the morning of the 5th. There aren't that many of them, but they will be quite bright. Now, for the northern Taurids, it's actually visible the entire month. Again, not a great number of them, but they're best seen near midnight and after. The king of the meteor showers for November is, of course, the Leonids, originating out of the constellation of Leo the Lion. They peak on the night of the 16th into the morning of the 17th. Now, the almost full moon will interfere with seeing some of the meteors, but the brightest ones will still be visible. And again, for the Leonids, they're best seen after midnight. And this is What's Up for November 2016. Thanks for watching.